is this. Or let me ask you a question. What does an atom look like? Okay, so I hear people talking about protons, neutrons, and electrons, right? You guys all know that those are in an atom?
Yes.
Okay, and those are subatomic particles. Does anybody know where to find those things? Okay, what's in the nucleus? Protons and neutrons, and where are the electrons? Okay, they're in a cloud. Where is that cloud? Inside the nucleus?
Outside.
Outside the nucleus. Okay, all right. And do you guys have any kind of, like, sense of the scale of those things in your mind?
Yes.
Okay, Jonathan, what's your sense of scale?
I think it was if you put like a head of a pin on a football field, that would be the nucleus, and then the electron cloud would be the rest of the stadium.
Okay, yeah, that's pretty good. I've heard the dime,
Yeah.
okay, but still, nonetheless, a very, very small object, let's say a dime. If you put a dime in the middle of the football field, that is the nucleus, and then if you take the football field, including the stadium, then that is the entire size of an atom. So, let me ask you this question. Where is most of the mass in the atom?
In the nucleus.
In the nucleus, that's right. What kind of mass does an electron have? It's like almost nothing. It takes a negligible, that's right, I know, it's a good word. Okay? If you take a few more than 1,800 electrons, you will start to get to the mass of a proton. It's like 1860 or something. Electrons equals the mass of a proton. Do we have any element that has 1,800 electrons in it? No. Okay. All right. So even in one of our biggest atoms, the mass of the electrons is still negligible. Okay. So virtually all the mass is in the nucleus. Okay. So tell me this: is the nucleus does it have a low density or a high density? Extremely high density. It's crazy. Like all the mass of an atom is in that dime. Yet, remember what is density? Mass over what? Volume. So where's most of the volume in the atom?
In the cloud.
The cloud. So we've got the dime. That's not very much of the volume that occupies the entire stadium. So isn't that crazy? That's why we call it an electron cloud. When you think of a cloud, don't you think of something that's not very dense? Okay, that's why we use that as the description. I've read this in a book I used to teach out of. It's kind of cool. Does anybody in here like to make fruit salad?
Yes.
Okay. And if you make fruit salad with like cantaloupe or a honeydew, any of those melons, they have this special spoon.
The baller.
It's called a melon baller, right? And you like scoop it out and you get these little balls of melon in there. Yum, yum, yum. Okay, good. Okay. All right. So I think of that, and I think of if you were to have like one of those that you could scoop the nucleus out of an atom, okay, and remove it, okay, and if you were to stick those nuclei in a matchbox, okay, we're talking small, the mass of that matchbox would be more than a collapsed star. I mean, that's just crazy. It'd be more than a star, more than a collapsed star. That's crazy.
I can't even fathom that.
I know. I mean, that is how dense the nucleus is. So it's actually very important that we have the electron cloud to balance out. You're right. If we talk about the density of an atom, then we've got the electron cloud in there as well. Okay. So here's the deal. The reason why I've been asking you to do the simulation of the hydrogen atom and to go back and read about these experiments is this. We kind of take for granted that atoms have protons, neutrons, and electrons, right? Mm-hmm. And we know, hi, we're so glad you're here. Just come on in. Okay? All right. Thanks. So we know that there are subatomic particles. We know there's a nucleus, etc. But if you think back, when you turned on your simulation, what was in the middle of the screen?
A question mark.
A box with a question mark. Well, we had no idea what an atom looked like. And even now, can we see an atom?
No.
No way. We don't have the microscopy that can go down that small. There's just no way. Okay? All we have is evidence. All we have is data that we gather. from these experiments that, oh my goodness, these brainiacs design, right? I mean, how do they even think of these experiments? Okay, but so we had no idea. We started to get an idea of an atom. You read about Dalton's atomic theory, really not a lot of experimental evidence at all, and then we moved further. Did anybody read about Rutherford's gold foil experiment? Okay, which is so cool. Did you guys get why they used gold?
Because it's malleable.
It is malleable. And malleable means you can pound it into a thin sheet, right? So that's what the foil is about, okay? Why did we want a very thin piece of anything? Metals will pound out into a thin piece, so that's why we chose a metal, okay? It didn't really matter that it was gold. But so why did we want a really thin piece? Does anybody know? Thank you. We didn't, you know what, we were trying to simulate having just a few atoms thick. We didn't want there to be so many, we wanted to try to, I mean, if we could have just had one target gold atom, that would have been perfect. But that was a little out of our realm of possibility. So we were trying to get a very small sample of atoms so we could get data on a microscopic scale, not this macro scale, just shooting things at a piece of metal, okay? And remember, Rutherford, actually they had to discover radioactivity, right? Once we figured out that there was this thing called radioactivity, he took the alpha particles that are positive and he just aimed them at the gold foil, okay? I read this in a book somewhere, it was kind of cool. When Rutherford set up the experiment, he really expected all the particles to just go right through. And did a lot bounce back? Just a few. Okay, if a lot were to have bounced back, what would our conclusion be about the nucleus of the atom?
They're bigger.
That it was big. Okay, not only was it massive, meaning it had a lot of weight or a lot of mass to it, it also would have been a bigger volume. Okay, but only a few bounced back. So that's why we have this idea of the nucleus being very, very small in terms of volume. Okay, but he expected them all to go through, and what he said, when those bounced back, it was like shooting a cannonball at a piece of tissue paper and having it bounce back. That's how unexpected the results were to him. And so when he saw those results, I mean, he was like, first of all, just blown away, and then they all just started scrambling and saying, what does this data mean? What can it tell us about what must have been in the gold atom to cause this to happen? So that's what we're kind of looking for, is how did this data of this invisible thing lead us to the conclusions that we have today? Okay? Now, the big picture is when we're talking about chemistry and chemical reactions, what subatomic particle do we care the most about?
Electrons.
The electrons. Why the electrons?
Because that's what help bonds.
That's how reactions happen, but why? Why is it the electrons that control?
Because they're on the outer.
I see Michelle go like this. Okay, yeah. They're the outer thing. They're the first things that are going to touch, right? Okay, they're the first things that are going to touch. And so that's why we care about the electrons. And of all the electrons, which ones do we care the most about?
Valence.
The valence electrons, right. Okay, so now what we're going to do, this is why today's such a funky day. I do want to talk about the simulation and all the scientists in a little bit more detail, but I think it'll be good for us to talk about electron configurations and go ahead and get some of that under our belt. Today was kind of a funky day with the career fair and people being in and out. And electron configurations, most people are starting to recognize. How many of you guys remember electron configurations from Chem 1? Okay, you might need to be reminded about some S and P things, okay, but you know that. So that's what we're going to do right now, okay.